these obstacles into the domain and you want to model it somehow. If you think, for example, inverse boundary methods or fictitious domain methods to get the idea. So what you can do is what I came across was the idea of blending these obstacles together with the fluid domain, in the sense of representing the obstacle by areas of very high or very low permeability. So in that sense, if you think about blending these two domains together, what we did is we model these obstacles now by introducing the so-called Darcy-Drake term, which penalizes basically by a very big, or that case inverse big permeability. And by that, actually where the permeability is big or low, sorry, inverse permeability is big, we can see that we can represent basically, we can penalize the flow velocity we are looking for in that areas. And this also, you see here in Navier-Stokes equations, this is simply done by adding this small term here, which is called the Darcy-Drake term. And the question remains, we now transformed representing the obstacle by finding the areas of low and high permeability. And this, of course, we also model the same for moving domains in case you have, for example, a moving heart. And this is now the same formulation stated in the arbitrary Lagrangian Eulerian formulation, or ALE formulation. How do we discretize that? So I'm working mostly with the software CARP that we heard before, the talk by Ed Wigman, one of the developers. And I'm also a developer for OpenCARP, and here especially responsible for developing CFD applications. What we do for discretizing this model I just showed you is we use a large eddy approach. Why do we do that? Because thinking of a direct numerical simulation would require, at the moment, still too high amounts of unknowns and degrees of freedom. So we need to model some sort of turbulence. And we use the so-called residual-based variation multiscale formulation, where we basically, it is a certain type of large eddy formulation, where we split up our unknown solution into a representable solution by the finite element method and then non-representable, thus modeled portion that will be modeled with element-wise residuals. The nice thing about this formulation is it acts as well as a stabilization as a turbulence model. It also allows for equal order finite elements, which is nice for our code. And in contrast to, for example, K epsilon models, when you do Reynolds average Navier-Stokes equation, it doesn't include any artificial equations. And it is also very straightforward, extendable to moving domains. For the time discretization, in all the simulations I'm presenting here, I'm using either an implicit generalized alpha or sometimes also semi-implicit backward distributed formulation. So the question I presented first was these areas of low and high permeability. If you're familiar with immerse boundary methods, you also need at some point to somehow immerse the obstacle or half-off or whatever you want to model into your computational domain. What we do is, if you immerse now, for example, if you think of a surface here on the left, this picture, what we do is by using KD trees and some techniques from ray tracing, we basically just calculate the fractional value of volume that is basically inside of the obstacle. So by that, we can calculate this volume fraction value VF, and then we can define this penalization parameter by just multiplying by the big number. This turns out to work quite nicely, and it works with moving objects as well as non-moving objects. In case of moving objects, we also have the capability to interpolate the velocity of the obstacle onto our computational domain. If you think about, in the beginning, I showed you this picture of this blood pump. If you think about immersing this into your software, and this is a rotating object, at some point, if you would use an ALE formulation, you would need to think about remeshing because your topology would change at some point. With this method here, we can just discretize one period of the motion or one turn of the motion. And second, we don't need to think about topological changes. And both this obstacle treatment we interpret as a pre-processing tool in the open source software mesh tool, which we published this year a nice paper about. So let me just give you two interesting applications that should highlight the work. So the first was, as you saw in my introductory picture, the FDA round-robin benchmark. So what was it was a benchmark study that was proposed by the FDA to simulate and basically validate CFD codes with respect to the simulation of blood flow driven by a blood pump. So it was a set of CAD files was provided, from which you see here in the top figure on the left. This is basically the computational setup, where you see in red the rotor disc that is mounted onto an engine, and this is driven by either 2,500 rounds per minute or 3,500 rounds per minute. And from top to bottom, there is an inflow of varying degree, and to the back you see the outflow. And basically, the benchmark consisted in validating the pressure drop between the in and the outflow. We used our obstacle representation, immersed this object into our computational mesh, which you see on the right. You see here the object a bit more opaque, and the red areas are basically the covered areas, and you see here a little in color difference. This means these are areas that are basically not exactly represented. And this is basically also rotating, so this is basically a varying field of permeability. We created a mesh and ran simulations for 20 revolutions of this rotor, and this was done on the VST4 cluster in Vienna with about 1,200 MPI processes, and it took around 20 seconds to calculate one time step, or in total 72 hours. And here are some results. As I told you, the validation. On the left top, you see the velocity field for one case. This is 6 liters per minute inflow. And the rotor, the blood pump, is rotating counterclockwise. So as you see, the velocity is biggest in the wake of the blades. And also the pressure is bigger in front of the blades and lower in the back. We also calculated the pressure differences that were measured by the FDA in experiments with PIV data. And we could confirm for all but one cases, we could confirm, or we could validate and state in the confidence interval provided for this data. The last case with 7 liters per minute inflow we were not able to validate. My assumption is that we have too low mesh resolution for that. And here you can see a video. This is a slowed down video of our result. I hope it plays at the right speed. I tested before on my laptop where it was running a bit slow. This video is basically a 25 times slowed down video of the original movement. So this rotates quite fast. What you see here depicted is the evolution of the velocity, the magnitude of the velocity field. And the second application, which is actually gave the title for my talk, was the simulation for a 4-chamber heart model. The data for this model was provided by colleagues at KCI. This was a 74-year-old male patient with a heart rate of 83 beats per minute. we had a CT scan available, and also we generated a model out of these CT scans, and also we were able to motion track and extract the motion of the heart out of cine CT scans. For that, we generated meshes from the segmented model for the left heart and the right heart. Since this is a prescribed motion, the left and the right side of the heart are actually separated from a CFD side of view, and we could run separate simulations. At the outlets, which you see here, for domains, we used Windcastle, 0D models, or constant pressure outlets. And you see here also, I hope you can see it, these are basically the areas which actually covered the valves. With that, we did 4 beats for each side of the heart, and this was done on the Archer cluster in the UK. Every of these simulations for 4 beats took less than 24 hours to complete. Here you see a result. Here you see the evolution of the velocity field in the left and the right heart. Now in this case, I put the simulations again together, so they look a bit more nice. But it was not only about generating a nice video, we also tried to validate these results against clinical data. So what we did is we sampled points in the domains, like in the left ventricle and in the aorta. So we put spheres in there and sample points and average the pressure values in these areas. And what you see in the top are the pressure curves from these averaged values. And according to the clinicians, we used the shaded area here for calculating the pressure difference. So there was a reported clinical measurement for the pressure difference for this patient, which was about 3 millimeters of mercury, which was extracted from an echo study. And we did the same. So this is basically the simulated pressure traces from the left ventricle and the aorta. And we calculated the same pressure difference, and we came up with 3.28 millimeters mercury, which is actually rather nice. And with that, I'd like to conclude. So the nice thing about this method we developed is, since it's modeled by a Darcy drag term, it actually has a nice physics backing. If you dig long enough in the literature, you find a lot of mathematical proofs of convergence if you increase the penalization parameter to infinity. It's very easy to be added to existing code. Of course, it's very relevant for studying, for example, rotating objects like turbines, but it also works, for example, for simulating the effect of a heart valve. Not the complex valve dynamics, but you can, if you want to just impede flow in certain areas of your domain, it works quite well. This is also the downsides. One of the problems with LES simulations, you have a mesh-dependent accuracy. The finer you resolve your mesh, the more things you see. And also, I simplified for the 4-chamber heart quite a lot, so there's no bidirectional feedback. So for future work, first of all, we submitted this method now for publication. I'm at the moment working on the sensitivity analysis and some uncertainty quantification, as you may well be aware that working with clinical data always is prone to a lot of uncertainties. And of course, there's a lot of applications possible for industrial applications like medical devices or program data optimizations. And I'm also working on valve dynamics. So with that, I would like to thank you for your attention and point you to our homepage for OpenCarb if you are interested in joining our project. Thanks a lot.
Thank you for your interesting and thoughtful presentation. I'm seeing there is questions. Well, there is a question from Professor Dussel. You can take the mic.
Yes, thank you. Thank you for this very interesting talk. But maybe I have missed that, but I didn't catch how you finally modeled the opening and the closing of the valve with your model of the permeability So is that is a time course that you find from imaging data or from is it really a porous opening and closing or?
Thanks for the question. Yes, we did the following. So basically, the area where the valve is basically just an area in the segmentation. Mm-hmm. So what I found is basically I calculated the opening and closing times from studying basically the changes of volume in the different compounds. And then I just interpolated between fully permeable and not permeable in this fraction of time when it's opening and closing.
Okay, thank you.
Thank you. There is another quick question from Professor Mittal.
Hi, great talk, very interesting work. So I had a question about the FDA benchmark that you were showing. Were you able to make some quantitative comparisons to some of the experimental data that's provided in benchmarks?
I was trying to find, like, the only papers I found was basically the pressure differences. So this was published. So I was digging through literature, I tried to validate the torque, which I put here in the table, but I didn't find any publications yet where they provided data for comparison. So I also have, I didn't include that here, I had some qualitative comparison about the velocity profiles along the some cuts, and most of them looked okay. But basically, the only thing I really can state that worked quite nice were the pressure differences. The rest I didn't found references to compare to.
Yeah, you might want to check the FDA website. I think they've provided all the data for comparison.
Yes, thank you.
Thanks.
Okay, thank you. And